In 2026, autonomous drones run our world. They inspect high-voltage power lines, map vast agricultural fields, and deliver cargo beyond visual line of sight. But when an enterprise UAV worth $50,000 suddenly drops from the sky, it doesn't leave a suicide note. It leaves a data flash log. To the untrained eye, a drone crash looks like bad luck or wind. To a UAV support engineer, it's a systematic sequence of digital events recorded at 50 Hz. Today, we are opening the black box. We are going to break down every major autonomous drone failure mode, look at the exact telemetry metrics behind them, and explain how engineers look at raw logs to pinpoint the exact millisecond everything went wrong. Let's look under the hood. First up, power infrastructure. The most deceptive failure here is the low-voltage brownout. During a high-stress maneuver, like fighting a 25-knot gust, the motors draw maximum current. If a single cell in a lithium polymer or solid-state battery degrades, its internal resistance spikes, causing a massive voltage sag. In the telemetry logs, we see the board voltage drops below the critical 4.5-volt threshold. Instantly, the flight controller undergoes a hardware reset mid-air. The log file just abruptly cuts off. No failsafe, no warning. Just an instant brick. The second power failure is the ESC synchronization loss. Brushless motors rely on the electronic speed controller to read the back electromotive force to know exactly when to switch phases. If there is a sudden mechanical load or a microfracture in the power wire, the ESC loses track of the rotor's position. In ArduPilot or PX4 logs, this shows up as a violent divergence. The desired roll or pitch graphs completely split from the actual roll and pitch data. The drone tries to compensate, sends a 100% duty cycle signal to the failing motor, undergoes a desync roll, and enters an unrecoverable flip. Next, we move to the drone sensors and the extended Kalman filter, or EKF. The EKF is the mathematical brain that fuses data from the IMU, GPS, and magnetometer to estimate the drone's actual position. If the sensors lie, the EKF panics. Let's look at mechanical vibrations. High-frequency vibrations from unbalanced carbon props or worn motor bearings leak into the accelerometer. In ArduPilot logs, we analyze this via the vibe message. Normal vibration levels stay under 30 meters per second squared. Once VibeX or VibeY spikes past 60, the EKF's altitude and position estimates drift away from reality. The drone loses its spatial orientation. To the pilot, it looks like the drone suddenly rocketed into the sky or drifted away in loiter mode. But in reality, the autopilot was just trying to correct an imaginary altitude drop caused by sensor clipping. Then there is magnetometer interference, famously known as toilet bowling. Commercial drones often fly near industrial steel structures or high-voltage lines that emit massive electromagnetic fields. This corrupts the compass heading. The EKF sees a massive variance between the GPS velocity vector and the compass heading. The drone begins to fly in aggressive, expanding circles, trying to resolve the mathematical paradox until it hits an obstacle or triggers a land failsafe. Now, let's talk about the digital umbilical cord, navigation, and signal loss. In autonomous operations, a GPS glitch can be catastrophic. If the drone suddenly loses line of sight to the satellites due to urban canyons or signal spoofing, the horizontal position accuracy drops instantly. The EKF flags a bad variance. If the drone is running an automated mission path, the autopilot triggers a failsafe. This brings us to the failsafe loop of death. If the GCS, the ground control station, loses the MAV-link telemetry link due to radio frequency interference, the drone is programmed to execute an RTL return to launch. It climbs to a preset altitude and flies back. But what if the compass is also glitching at that exact moment? The drone enters an RTL loop, attempts to navigate home blindly, drifts due to the compass error, breaches its geofence boundary, and is forced into an immediate emergency autoland, regardless of what is directly beneath it, be it water, a highway, or dense forest. Diagnosing these errors is what separates amateur pilots from professional UAV engineers. Every single crash tells a story through voltage drops, vibration spikes, and EKF innovations. By understanding how to read these data flash logs and analyze MAV-link packets, we can prevent future failures, optimize industrial fleet deployments, and make autonomous flight truly bulletproof. If you want to dive deeper into the code, learn how to parse raw telemetry logs using Wireshark, or see real crash case studies broken down graph by graph, hit the subscribe button. This is BlackBox UAV. Drop your technical questions in the comments below, and I'll see you in the next data dump. Clear skies.